Hello everyone, today I'm here to conduct our lab experiment 2, which is series and parallel pump test. I want to start with the objective of the experiment. The purpose of this experiment is to determine characteristics of a centrifugal pumps for single, series and parallel configurations. At the end, we will determine their required powers for different configurations. Now I want to talk about a bit the theory part of the experiment too. Here in lab manual you can see there is a image given for the pump to us. In this image there are 4 parts for the pump. Part 1 is the angled blades, part 2 is the helical housing, part 3 is the delivery pipe, and part 4 is the intake branch. In a centrifugal pump like this, the liquid is driven by angled blades, which rotates in a helical housing. The water is accelerated by centrifugal force and fed into delivery pipe. The outpouring of the water creates a negative pressure at the intake branch and the water is sucked through the connected intake pipe. Centrifugal pumps generate a uniform volumetric flow without pressure surges. If we assume there is no loss, by using extended Bernoulli equation, we can get this expression. Here you see there is Pi, Vi, Zi, and Pe, Ve, Ze. Pi is the pump pressure at the entrance of the pump, and Pe is the pump pressure at the exit of the pump. Like that, similar to that, Vi is the velocity at the beginning and Ve is the velocity at the end of the pump. And Zi is the velocity, elevation head at the beginning, and Ze is the elevation head at the end of the pump. And we here the pump head. If we consider mass balance for liquids, the velocity at the section and the discharge is related to the respective cross-sectional areas, and that consideration gives us this equation. This is rho times AIVI will be equal to rho times AEVE. This is the cross-sectional area at the entrance, velocity at the entrance, cross-sectional area at the end, and velocity at the end of the pump. This expression suggests that volumetric flow rate, which is V dot, will be equal to cross-sectional area times velocity, and it will be constant through the experimental setup. If we neglect the elevation difference, which was Ze minus Zi, and change in area, which was cross-sectional area at the end and cross-sectional area at the beginning of the pump brings the following head input to the flow field. When we neglect the elevation head differences and the cross-sectional area differences, so we will basically cancelling this Vi, velocity head at the beginning with velocity at the end, and elevation head at the beginning with elevation at the end. So we are going to left with this one, pump head, and this one. And when we arrange it, we are going to get this pump head equation, Pi minus Pe minus Pi divided by rho g. Rho g is basically gamma. When we come to the pump power, which is shown as W dot pump, the total power transferred to the fluid for volumetric flow rate, which was V dot, can be expressed as rho g times flow rate times pump head. And we know from here pump head was Pe minus Pi divided by rho g. So this rho g and that rho g will cancel each other when we write this expression instead of pump head here. This rho g and this rho g will cancel each other, and we are going to left with flow rate times Pe minus Pi. For centrifugal pumps, the delivered volumetric flow rate is related to the pressure difference which the pump has to generate within a pipe network. If the required pump pressure is high, the resulting volumetric flow will be low. And if pump pressure is low, the required volumetric flow will be high. You can see that from this pump curve provided us. Look at here, when our volumetric flow is low, we have very high pump pressure. When pump pressure is getting decreased, at the same time we are getting higher and higher volumetric flows. These correlations between pump pressure and volumetric flow gives us this delta P. Delta P will be equal to PE minus PI, which is the pressure at the end and pressure at the beginning for the pump. When we want to combine two pumps in series, the volumetric flow rate will be same through the pumps. The pump characteristic curves will be steeper. At the end, to get total pressure head difference, we are going to sum the delta P for pump 1 and delta P for pump 2. On the other hand, when we connect two pumps in parallel, the achievable pump pressure difference becomes the same for both pumps. In other words, with the identical pressure differences, a higher volumetric flow can be delivered. And at the end, we will get this equation. We will use this equation for pumps in parallels. We will sum flow rate for pump 1 and flow rate for pump 2. As a side note, we should not operate dissimilar sized pumps in parallel.
Before I start the experimentation, I want to introduce you the device which we are going to use during this experiment. This is our pump device. We have a water tank here. When I turn on this device from this green button, water will start raising in this tank. And we have switches for pumps. This is switch for pump 1 and this is the switch for pump 2. When I turn this on and this, water level will start decreasing in this tank. Apart from those two, we have different valves for these pipes. We have two main valves. This is our main inlet and this is our main outlet valves. We have two pumps, as I said. This is our pump 1 and this is our pump 2. And we have two barometers attached to those pumps. First barometer gives us the inlet pressure on this pump, and the second barometer gives us the outlet pressure for the first pump. And we have two barometers here as well. First one shows us the inlet pressure for pump 2, and this one shows us the outlet pressure for pump 2. At the end of each measurement, we will come here and we have another water tank. This should be opened normally during the experiment, but as you know, we want to measure our discharge. To do that, by closing this pump, water level will start increasing in this tube. This is in liters. I will measure from 10 liters to 20 liters and record the time. By using those two records, we can get our discharge. Now I want to show you required setup for three different configurations. I want to start with the single pump test. For single pump test, since we have equal pumps, we are going to use only pump 1 and that will be enough for us. For single pump test, we have to let water come from this tank through this pipe. From here, it will let in the pump, get out, and we want it to follow this path. And it will go out from the system. so that we want to open this main inlet valve and this valve and that main outlet. When the setup is like this, it means we are going to perform a single pump test. For a series pump test, this time we want water to come through the tank, follow this pipe, come here. We want it to go through the pump 2, follow this path, and then go out. Therefore, we need to close this valve because we want water to go through this side. And we need to open this valve and that valve, like this. And lastly, for the parallel configuration, we want water to come through 2 different pipes. So we need to open this valve as well. They will come. This valve from this side, it will go through pump 1 and come here. And for this side, it will go through pump 1 or 2 and come here, and they will meet here. Therefore, we need to close this shared valve, and it will be enough for our parallel configuration. I want to perform the real experiment for you. I will start with the single pump test, then I will continue with the series, and I will finish with the parallel pump test. For single pump test, as I explained, water will come from here and follow this path. So this valve, and that valve will be open. Now I will turn on the system and water level will start raising in this tank. Up to some point, I will let it increase. Then I will switch this pump 1 from each switch. Water will still continue to increase, but it will increase in a slower speed. Then it will come here at the end and go back up to this red sign. Now let me switch on. You see water level is increasing. Now I will turn on the pump 1. Now it should come back. We need to wait till its level here. It might go up and come back couple times. So I will wait around 15 seconds. Okay, it seems good. Now, you see these valves are fully open. When I start changing the discharge, for example from here, when I change it, you can see the pressure in this inlet for the pump 1 is changing as well. And when I change the discharge from here, pressure for the outlet of pump 1 is changing as well. And this was the for pump 1. At the end, when I took my measurements, I will come here, close the valve for this pump, for this tank, and wait. Water level come to 10 liters, and I will start measuring here, and I will wait till it reaches 20 liters. Like this. Then I will stop, open this valve again. I want to continue with the series configurations. For series, as I said, water will come through this pipe, go through this one, come here. Here we will go through pump 2, and it will get out from the outlet. Now I'm turning on the system again. This time, since we are gonna use two pumps, I need to switch them both. And I will wait again till it levels here. It seems like it leveled. Now, you see we have pressure here, and when I start changing this discharge, we will have outlet pressures here as well. And we have two different pressure numbers for pump 2. This is inlet pressure for pump 2, and this is outlet pressure for pump 2. And at the end, again, I will take time required to fill this tank for 10 liters, and I will you will be able to calculate the discharge. Now I want to perform our last configuration type, which is parallel. For parallel, water will come from both pipes. For the first pump, it will come here and follow this path. And for the second pump, I also need to open this valve. It will come from here and follow this path. Now I'm turning on the system. And again we are going to use both pumps, so I will switch them both. And since they are equal, their pressure numbers, inlet and outlet, must be equal. So now water is level, and I set the system already. So these are the numbers for pump 2, inlet and outlet, and these are the numbers for pump. This was pump 1, and these are the numbers for pump 2, inlet and outlet. You can see numbers are very close to each other, and it should be that way because in parallel configurations, since the pumps are same exactly, the pressure numbers must be also same.
Now I would like to give you some brief information about what to expect you to do in your lab reports. If you turn on page number 3 of your handouts, you will see that there is an analysis part. If we look at this part, first of all, we want you to plot characteristic curves for all single, series, and parallel configurations in one graph. You need to put total pressure difference to the vertical axis and flow rate to the horizontal axis. Secondly, we want you to calculate power consumption by each pump for all the data collected and plot another graph as power versus flow rate. Lastly, apart from those two things I mentioned, right below the analysis part, you are given some report questions and important things to be mentioned in your report. We also want you to answer those report questions and explain the things asked in this part.